Hello guys, welcome to lesson number 6. This is on related rates. I love this lesson. It's one of my favorite lessons of the course. I think it's great because it takes implicit differentiation and applies it to real life applications. I will tell you guys that there are so many related rate questions that can be done. I mean, I could spend 55, 105 videos on related rates. And there's so many types that you can do. So I'm just giving you guys some comfort that whatever's in these videos for this lesson and then what's in the homework is what you're going to be assessed on. So if you don't see it in the videos and you don't see it in the homework, then you're not going to be assessed on it. So here's what we do. We're going to do 3 videos for related rates. The first one is just going to be 3 standard ones, and this is the rules or how you do them. I will show you guys, instead of reading all this out to you, I'm just going to show you how I do it because I think it'd just be easier to do it that way. So let us start with question number 1. We always want to go pretty basic on the first question. And so what I tend to do is I read the question, obviously, and then I figure out what equation do I need to apply this question for. So and then I got other steps after that. So it says air is being pumped into a spherical balloon so that the volume increases. So I look at 2 words right there. 2 words just stood out to me. So air is being pumped into a spherical balloon so that its volume increases at a rate of 400 cubic centimeters per second. So I want a volume of a sphere, right? I want a volume of a sphere. So that's pretty much what I'm thinking I need to do. How fast is the radius of the balloon increasing when the diameter is 60 centimeters? Okay, so the first thing that I personally do is I write out the equation for the volume of a sphere. Now, I will give you some very happy news, okay? You are not required to know volume or area or surface area of a lot of the 3-dimensional shapes, like a cylinder, a cone, a sphere. I will provide those for you because the exam usually provides those for you. So sometimes the equation is basically given to you. So that first step is pretty easy. But anyways, here's the volume. I'm telling my students you do not need to know this equation. I would give it to you. All right, because we're not in geometry anymore. All right, so the next thing that I do over to the side is I say, okay, well, I looked at there's 2 variables here. I got a volume and I've got a radius. I got a volume and a radius. Well, I already know that the volume is increasing. So increasing means that it's positive at a rate of 400 cubic centimeters. Another thing is if I wasn't given the word volume, if it just says that a spherical balloon is being pumped so that it's increased at a rate of 400 cubic centimeters, I know this is a volume. Because remember, volume from geometry is always cube. So I know that this is a 3, it's a volume. If it's a square, I know it's an area. So that's a really awesome thing to remember from geometry. So I know that since it's increasing at a rate of, I know that the change of volume with respect to time, right, and that's going to be equal to 400 cubic centimeters per second. So the cubic centimeters is the change in volume, and the seconds is in the time. So that's how we know that we have the units correct. And it's asked, how fast is the radius increasing? Okay, how fast is the radius increasing? So I'm looking for the change in the radius with respect to time. That I do not know, but it's telling me when my diameter is equal to 60. All right, so the diameter is equal to 60 centimeters. So that means that my radius is going to be equal to 30 centimeters. All right, so this is the second thing that I do. So once I have my equation, I start going over what do I need, what do I have. So I read the question and I basically take it apart really and just get over here what I need to do. All right, so now what I end up doing is you have to now implicitly differentiate this, okay, with respect to time. So every variable is for me with respect to time. So v is the same thing as x. It's the same thing as y. So if you're taking the derivative of 1v, you're going to get 1, but now it's going to be the change in volume with respect to time. This is what a derivative is, ladies and gentlemen. It is change by rate of time. All right. So my change of volume with respect to time is equal to. Now remember, I have a number and I've got a variable to a power. It's the same thing. Do not confuse yourself. It's the same thing if I ask you guys to find the derivative of 5x cubed. You have a number. 4/3 pi is a number. You have a variable and you have a exponent. So you're going to move the 3 down and you're going to multiply 4/3 times 3, which is just going to be 4. You're going to do pi. And then we're going to do r to the 1 less power. Now remember, we took the derivative of the radius with respect to time. So we have to now do dr dt. So every time that you take the derivative of a variable with respect to time, you must always do this. You must always do this. If it's changing with time. And you can think about, if a balloon is blowing up, then yes, the radius of the balloon is changing, and so is the volume. There's an example that we're going to do a little bit later on where not everything changes, and so we can immediately plug right in. Okay, that's why I wasn't able to plug the 30 in right now, because the radius changes as the further I blow the balloon up. Now, once I get to this step, then I start plugging in what I know. And hopefully, if I've done this part correctly, I should be able to plug in everything here except for one thing. So do I know the change in my volume? Yes, it's right here. So I know this. Good. Do I know what the radius is now? Yes, I want to know what's the change at 30 centimeters. So I know that's good. And I need to find this out. And that's perfect. So I've got 3 unknowns in this equation, but I was given 2 of them in the problem. So I know that 400 is equal to 4t 30 squared dr dt. You want to be careful if it's an FRQ to keep the notation. Don't make this an r or an x. You want to leave it to dr over dt, okay? And so this would be a non-calculator question. Now technically you could set this equal, again, if this were an FRQ, by the way, I would highly encourage you to do this. I would absolutely encourage you just to leave it like that. That's all you have to do for this. But let's pretend like this is a multiple choice question. Okay, it's multiple choice, and they actually give you a value for it. So it's not that hard to do in your head, or at least I don't think it is. So I'm going to divide by 4. If I divide by 4, this is going to become 100. Right? And I'm going to go ahead and divide by pi. So really what I did is 400 divided by 4 pi. Right? So that gets rid of this. And there we go. So this goes in 100 times. So that's why that's right there. And then 30 squared is the same thing as 3 squared. Just add another 2 zeros to it. And so it's going to be 900. All right. So then that's going to be dr over dt. And so now I'm going to do 100 divided by 900, which is just 1/9. And I still got my pi. And then my units, because it's a change in radius, well, the radius is centimeters. Okay, and then it's going to be per second. So remember that units are really important in calculus. And so don't confuse yourself over the units. Volume is always going to be a cubed. Area is going to be a square. Anything else, it's going to be a singleton. It's going to be a 1. So if this is a change in height, a change in width, a change in length, it's all going to be 1 up here. And then you're going to use the same units for time as you're given in the problem. Okay? So example number 1, we are good to go. Let's look at example number 2. Now, if you have me last year in AB Calculus or even Miss Wollenbrock, then you know that you've seen this exact problem before. We just like it's classic. It's a classic question. Because it's a little bit mean, right? It's a little bit mean on this. It's the classic ladder question. You will have a homework question in your book about it. But what this is saying is that I have Tweety is resting in a birdhouse 24 feet above the ground. So you always want to assume in related rates, okay, you always want to assume in related rates that everything is perpendicular to the ground, and that is always true, unless otherwise stated. All right, so we have our pole that's 24 feet above the ground, and then we're going to use a 26, I apologize for my horrible drawing. So we have a ladder that's really bad, but it's okay. That's 26 feet, and it's leaning against the pole, holding the birdhouse. So again, this is perpendicular, so we go ahead and put ourselves a little guy right here. And Sylvester tries to steal the yellow bird away. So really quickly, what I want to highlight here is we have a right triangle, right? A right triangle where the hypotenuse is 26. Right now, this height is 24, and this would be our unknown side, which we could easily find using Pythagorean theorem. Why this is tricky is the next part. So Hector the dog, and I'm not even going to try to draw a dog, okay? So Hector the dog starts to pull the base of the ladder away. Before I continue on with that, I wanted to say that I create this, I make this my X, my Y, and my z, right? Because I know it's a right triangle, and I can relate these three sides together by our good friend Pythagorean theorem, right? So I know through this question that I'm going to use Pythagorean theorem. I probably got a little ahead of myself with that, but yeah. So let's continue on with the problem. So Hector the dog starts to pull the base of the ladder away at the pole at a rate of 2 feet per second. So you got to figure out what this is a change of. So I'll go ahead in my picture. I'd like to label things X, Y, Z or A, B, C, whatever it is. Because if I have the dog, so I'm just going to write the dog. So the dog's here, and he starts to pull the ladder away from the base, right? Pull the base of the ladder, which is right here, away from the pole, away from the pole. So that's this distance. It's getting bigger, right? It's getting bigger. So if you imagine the pole coming out, X is getting bigger. So the change in X with respect to time is equal to 2 feet per second. Okay, because again, you guys can visualize the ladder coming out, right? It's coming out, and again, the X is changing. This distance is changing with respect to time. All right. How fast is the ladder falling? So a key word here, falling. That means the ladder's falling. So that's going to be this distance right here. Like as the ladder goes down again and again. So my change in Y with respect to T, that's going to be my unknown when it's 10 feet from the base of the pole. So when the ladder is 10 feet from the base of the pole. So this is why this is a little bit mean question, because now I'm going to change. I want to know when the ladder is not at the top, but when it's literally at 10 feet. So let me actually pause this and draw this a little bit better for you. Okay, so I try to draw this as best as I can. And that now the dog has pulled the ladder further away from the pole, so X is now bigger, to the point what's happening. Our question's asking us how fast is the ladder falling when it's 10 feet. The height of the ladder is 10 feet from the base. So what you guys can now see is, and if I draw this triangle, this right triangle, now this is the 10 and this is the 26. And you can use Pythagorean theorem to actually find this side right here. Okay, but we'll get to that in a little bit of time. So here's our equation. We have a equation that represents how X, how Y, and how Z are related. And it's Pythagorean theorem because, again, we're making the assumption on all of these related rate questions that it's perpendicular to the ground. So let's do this. So here, right now, these are the only numbers, and then it says when it's 10 feet from the pole. So that means that Y is 10. Okay, Y is 10. And we also know that Z is going to be equal to the length of the ladder, which is going to be 26. And then using Pythagorean theorem, you know that X is going to be equal to 24. Okay, so those are our problems. So we have our equation, which is always step one. Our second step is always to kind of write over here to the side what we have. The third step is to implicitly differentiate this. And so let's go ahead and do that. When I do this problem, I'm going to have 2x. Now guys, this is where it's important. Everything's related to time. So it's not dx over dx like we talked about implicit. It's the change in x with respect to time. Everything's with respect to time here. So any variable, and there are 3 of them. So you're going to have 3 d somethings over dt's. So then we're going to do plus. You're going to do 2y squared. Well, that's the same thing as 2y. It's going to be dy dt. And you're going to have 2z dz dt. Now, I tell students all the time, so I've now successfully implicitly differentiated my equation. I do tell students that when you're doing Pythagorean theorem, you can always just write this out. It's just x dx dt plus y dy dt equals z dz dt. Okay, because the 2's are going to go away, and we don't need to worry about that. All right, so now step 4 is to make sure that we have everything, and then step 5 is to solve and to plug in and solve. So, do we have x, right? Do we have x? And yes, we do. We know x is 24. Do we know what dy dt is? Yes, we know. We know it's 2. Do we know what y is? Well, we found that by the problem itself, so this is 10. We do not know what dy dt is, right? Dy dt, I'm not sure what that is. We know that z is 26, and then we get over here and like, oh wait, we don't know what dz over dt is. Okay, we're not given that. But if we use some common sense, remember, as this ladder is going down this wall, this distance is changing. This distance is changing. but this is never changing. It's a ladder, right? It's a ladder. So it's not going to change. So dz dt is just going to be equal to 0. This is a constant, right? The ladder is just going to come down the ladder. It's not retractable. We're assuming that. So it's going to be 0. So then what we have left in this final part of the problem is we say, okay, well, this is 48 plus 10 dy dt is equal to 0. And again, ladies and gentlemen, dy dt is going to be equal to negative 48 over 10. And that is just negative 4.8. Again, this is okay as an answer for an FRQ. Most likely be negative 4.8. And then we go back to their units. So it's by feet per second. All right, it's feet per second. And our answer makes sense. Even if it didn't have the word falling up here, our answer makes sense because this distance is getting smaller. As the ladder's coming down, the change in y is getting smaller. So now you guys can appreciate when you see a derivative that is negative, that means the rate of change is decreasing, right? We're losing a rate faster, okay? Hopefully that will make sense to you. All right, let's do example number 3. This is one of the most fun ones. It does require a little bit more thinking, but again, I know you guys can handle it. So let's get to it. All right, so a water tank has a shape of an inverted circular cone. So let's go ahead and do a circular cone like so. Boom, yeah. And it has a base radius of 2. So a base radius of 2 meters and a height of 4 meters. Okay. The water is being pumped into the tank at a rate of, all right, so our water is being pumped into the tank at a rate of 2 meters cubed or cubic meters per minute. So we know based on the fact that there's a cube here that that's a change in volume. We know that that is a change in volume. We also know that this is positive because it's being pumped into the tank. If this said the water is being pumped out of the tank, then we would have to do a negative 2 here. They're not going to tell you it's negative, so just use some not common sense, but just think about it for a second and think about, okay, if water is being pumped into this tank, then the volume of water is increasing as I go through more time, right? The more I get it, the more water we get. So that's why that's positive. Find the rate at which the water level is rising. Okay, so now what is that? The water level is rising. Well, that's a change in height. So I want to know what this, all right. And again, it's rate, the rate, so the change in height with respect to time. And it's asking us, when is the water level rising? When the water is 3 meters deep. So one of the things I would suggest maybe doing first when you guys do these problems is read the question first, just through, and then start drawing your diagram and then start thinking about stuff like this, right? I think it's easier to do it that way, to just read it first, get a feel for what the question's asking, and then start kind of breaking it apart. So the equation that you guys have to know, and actually it's going to be given to you, all right? So there we go. So the volume of a cone is 1/3 pi r squared h. So what we have to think about first is, can we plug something in initially? Because a lot of students are like, oh, well, the height's 3. Let's go ahead and plug in the 3 for height. You can't do that here. You can't do that here because as my water level is rising, the height is changing and so is the radius. So when my water level is right here in the cone, then the radius is this distance here. But then when the water level is at this level of the cone, then again, the radius is changing. So is the height. So you can't substitute anything in normally. Now there's an example that we do in my AB class that I'm not going to do here, but we talk about a well who's got a little hole in it, and so as we're filling up the well, it's a rectangular well, so as we fill it up, the length and the width does not change. So when you look at the volume equals length times width times height, you can go ahead and plug in what the length and the width are because they don't change with respect to this well. But in a cone, it does change. Okay, it does change. Okay, so I'm going to purposely do something wrong. I'm going to show you guys how to do this implicitly, and then we're going to have a little bit of an issue with this problem, and then we're going to come back and fix it. All right, so the first thing I'm going to say, okay, well, let's go ahead and implicitly differentiate this because I can't plug anything in. So I get dv over dt is equal to, please don't write this down because this is going to be wrong, so you just kind of look at this. So I got the 1/3, and like, oh my god, we have to use the product rule. Right, we have to use the product rule here. We have two functions. That's why I really, really want to talk about that here for a second. So the radius, we're going to do first times the derivative of the second plus the second times the derivative of the first. Okay? So this is what you would have to do. And so normally you'd be like, oh, this is awesome, that's great. Well, do we have the change in the volume? Yes. Do we have what the radius is? Well, we kind of can assume that. We know when the height's 3, we have a relationship to get the radius. So yeah, we can find that. The height, the change in height is what we're trying to find. We know what the height is. Again, it's 3. We can easily find the radius. But guys, we don't know what this is. We have no idea what the change in the radius is. There's nothing here that tells us that. So we do the problem this way. We have 2 unknowns and we only have 1 equation. And so you guys know that you cannot solve the 2 unknowns with 1 equation. Right? You have to be able to do 1 equation with 1 unknown. Okay? So that is not correct. So what can we do? Well, we need to get rid of one of these variables. We need to get rid of one of these variables. So what I was kind of talking about before is that this is the radius and this is the height. So I told you guys, oh yeah, we could find the radius. Well, this is how you do it. So the radius over height, it's got a ratio, right? So this is a proportion from, again, geometry of 2 to 4. So the radius is always half of the height. If the overall big thing is 2, this is going to be 4. Well, then when the radius is 1, this height's going to be 2. So we have this awesome relationship, this proportion of r over h is equal to 2 over 4. Trying to find the change in height. So what we need to do is we need to solve for the radius. And you guys will understand here in a second why. I need to find the radius. So I get that the radius is going to be 1/2 height. And we just talked about that. We just said that the radius is always 1/2 height. I know this is always true because this proportion has to hold up the entire cone. So I can now substitute for my radius as 1/2 height, because that's what the radius is equal to. So when you guys are given a question like this cone question, you're always going to find, using a simple proportion, the ratio of this. If this had been a 3 and a 9, then it'd be a 1/3 here. So again, don't assume it's always 1/2. Now let's simplify this a little bit more. Notice I'm not taking any derivatives, I'm just simplifying it. So I'm going to get 1/3 pi. This is going to be 1/2 squared, so it's 1/4 h squared h. And so our final equation before we start implicitly differentiating is 1/12 pi h cubed. So take a second and make sure that you understand what I did here. I took the equation and then I realized that if I were to implicitly differentiate this initially, I have 2 unknowns, 1 variable. Sorry, 2 unknowns, 1 equation. Can't solve that. So then I had to think cleverly, how can I get rid of one of these? Why did I solve for r and not h? Because I need to get rid of r because I know what the change in h is. So once you do this, now we can start taking the derivative of this implicitly. So change in my volume with respect to time is equal to, again, we have a number, so this is example number 1 again. We have a number to a variable to an exponent. So we move the 3 down, and so we're going to multiply 3 times 1/12, which is really 1/4, but let's leave it 3 over 12 right now. Leave pi alone, because that's just a number. We have h squared, and then the dh dt. So hopefully this is where you start understanding, if you haven't already done so, why I had to solve for r. Why did I have to get rid of r? Because I needed to incorporate the delta change in height over change in t in my problem. Because now, look at this, I've got 3 unknowns. Well, I know what my volume is, I know what my height is, and now I'm just finding my delta, my change in my height. So I'm good here. I can now substitute in my problem. So I know that this is going to be 2. This is going to be 1/4 pi. My height is going to be 3 squared dh dt. So now it's just a substitution problem. So I'm going to go ahead and multiply both sides by 4, and I'm going to get an 8, right? And so I've got a 9 pi here, a 9 pi, so I'm going to go ahead and divide by 9 pi. And that's going to give me the change in height with respect to time. All right? And the only thing that I have left to do here is just put my units on there. Since this is a change in height, it's not an area, it's not a volume. I know that I just come up here, it's just meters. So actually, let's write it like this. So 8/9 pi meters per, and then again, we're looking at minutes, the time minutes. Okay? So those are our first 3 types of related rates. So I have 5 steps. Again, what I do is I have the equation. I write the equation up. Step 2 is for me to kind of do a little sidetrack here of what I have, what do I need. The third step is to implicitly differentiate. So 3 is the most important thing, using implicit differentiation. Step 4 is to plug in what I know, and step 5 is to solve and write the units. All right, so let's come back in the next video, and we will do more types of related rates that I would expect you guys to know in class. See you later.